Okay, so this is for Monday, January 31st, which is now an asynchronous day. So your assignment is to complete the file in the folder, which is in the Unit 5 folder. And day one, it's a warm-up and a solving review. So don't forget that the original lesson videos from Magna Advanced Algebra are in the last day of the parametric folders. I might move them over to, or copy them over to the day one folder in Unit 5 as well, just so they're easier to find. So this is meant to just, if you are struggling at all, it's just meant to sort of help you. I'm going to do some of the problems and give some hints about some of the others, but I will be checking that everything is done when I see you next class. Okay, so the first section is write the log equation in exponential form. So a couple things that you can remember is that the base of the log will also be the base of the exponent. Okay, so it's the base in either form. So if I'm writing this in exponential form, 4 is the base to the exponent, and then the other two values are just going to switch sides of the equal sign. So the 3 will become the exponent, and the 64 will be in the right-hand side. And if you're going from log form to exponential form, then there's a little bit of a checking factor there, because I can see that, yes, 4 cubed does equal 64. So probably right. For number 3, just remember that when you see natural log, that means the base is e. Also, if you see a log with no base written, it's a common log and the base is 10. So you'll either see the base written, or if it's natural log, the base is e, or if you see log but no base written, then it's a common log and the base is 10. Okay, so then the next section, we're writing the exponential equation in log form. So we're going the other way. So again, the base is the base in either form. So I'm trying to write it in log form. The base of the exponent is the base of the log. The other two values are going to swap sides. So the 125 is going to be the value next to the log, and the 3 will be the right-hand side. This doesn't really have the same kind of checking factor that it does when you go to exponential form, because our brains aren't great at understanding a logarithm when we see it. We can understand the exponential equation because we have enough experience with them, but not so much with the log version. So as I mentioned before, just remember when you see e, that in log form, that would be written as natural log. Log base e is natural log. The next section, we are expanding. So from the notes that you picked up after the parametrics quiz, it had the properties of logs, which have a direct tie-in to the properties of exponents. But if we are expanding, that means that we are taking multiplication to addition. We're taking division to subtraction, and we're taking exponents to coefficients. So our expanded version has addition, subtraction, and coefficients. It doesn't mean that those other things can't still be present, but that is the way that we're going. Okay, so we have a natural log. And inside the brackets, we have a couple things happening. We have x being multiplied times the quantity of x minus 1, and we also have an exponent. So the multiplication is going to break up into addition. So that means since I have two things being multiplied, then each of those things are going to get its own natural log, and I'm going to connect those logs with the addition, because multiplication turns into addition. And then I don't have any division. You don't expand subtraction to anything. You are going from multiplication, from division, or from exponents. If you already have addition, subtraction, coefficients, then chances are they're not going to change. But I do have an exponent and an expanded form. That should be a coefficient. So I'm going to take that log and I'm going to write that exponent out front. And that is considered fully expanded. In number 8, I have two things being divided. So division expands to subtraction. So the numerator gets a log, or a natural log in this case, and the denominator does as well. And I'm going to connect those two natural logs with subtraction. So I'm done over here. Here, I've got some more work to do. We don't actually have any properties of logs that address radicals, but we should know that any radicals can be written as a rational exponent, and a square root is the same as a 1/2 power. Those have the same exact meaning. And then again, if you have an exponent, part of expanding is to write it as a coefficient, which just moves it out front of the natural log. So we still have an exponent and we have some addition. We don't expand addition to anything. And this exponent is part of this quantity. So I can't break that up at all. I could keep going and work just with this and break this up more. I'm going to leave it like that though. So then you have those two to do. The next section is condensing. So we're going the other way. So if we are condensing, notice it says single logarithm. That's super important. If you're asked to condense something and you have more than one logarithm in your answer, then it's not right. So we're going the other way. We're going to condense addition to multiplication. We're going to condense subtraction to division. And we're going to condense coefficients to exponents. Okay, so we want to end up with multiplication, division, and exponents instead of addition, subtraction, and coefficients. So we have two logs. Each of them have a coefficient. So we're going to kind of go in reverse order of operations. We're going to take the coefficients and we're going to move them up as exponents first. So it's going to become natural log of 8 squared plus natural log of z to the 5th. And then I can clean this up right here. I can call that natural log of 64 plus natural log of z to the 5th. I still have two natural logs that are added, and addition should condense to multiplication, so it should be a single logarithm. And addition changes to multiplication, so it's going to be 64z to the 5th. All right, so for this one, I have one coefficient. So the first thing I'll do is change that to an exponent. And then I have two natural logs subtracted. Subtraction changed to division. It's a single logarithm. So x will become the numerator, and the quantity of x plus 1 cubed will become the denominator. All right, so then you still have these two from that section. So the next section is solving. So you had work to do after the parametrics quiz to practice with solving. From the original lesson from my advanced algebra, we kind of break those up into sections, types of equations. So we have exponential and we have logarithmic. Okay, so the exponential, one type of exponential is it is possible to do some rewriting to make the bases match. So 3's prime, I'm not going to rewrite that. That's going to stay the way it is. So that's going to stay as 3 to the 1 minus 2x power. But I can rewrite 243 with the same base as I have over here, because 243 is 3 to the 5th power. And once the bases match, I can cross those out and I can set the exponents equal. The idea is if the bases are equal, then the exponents must be equal as well. And then I'm just solving for x. So I'm going to subtract 1 from both sides and divide by -2. Okay, so this would be the same thing. Get the bases the same. 3, 4, 5, they're all similar. It is still going to be exponential where you're trying to get the bases the same, but we have a little more going on. So we're going to involve our exponent rules. So over here on number 4, I'm just going to work on the left. I could get the same base across the board right from the beginning, but I'm going to concentrate on the left because I need it to be like just, base equals base. And I've got a little more going over here on the left, as you can see is happening in 3 and 5. So what would be easier for me if I'm just looking at the left-hand side is to write 81 as 9 squared. And then I have another base of 9. The exponent is negative 2x minus 2. And again, still just trying to work on simplifying the left-hand side. So exponent rules say, if the bases are the same and you are subtracting, you should add your exponents. So that would become 9 to the 2 plus negative 2x minus 2 power. Bases are the same, you're multiplying, add exponents. So the 2 is going to cancel out 2 and negative 2, so that's just 9 to the negative 2x. All right, now that I've simplified the left-hand side, now I'm going to worry about going back to the beginning and trying to rewrite both sides in this case so that the bases match. I can't rewrite 27 to have a base of 9. And you're never going to be writing a smaller base to match a bigger base. So I'm going to have to do something to both sides. Both sides can be written with a base of 3. Almost messed that up, common error. So 9 is 3 squared and 27 is 3 cubed. Now the bases match. I can cross them out. I have 2 times negative 2x is negative 4x equals 3. So x equals negative 3/4. Okay, so again, 3 and 5 would be similar to that. I'm not going to do number 6 for you, but we do need to get the bases to match. So if you're going to use your exponential equation strategies, try and be creative. Is there a way that I can rewrite 1 with a base of 4? Well, 4 to what power would equal 1? Got to think about that. All right, so then this is just more of the same, trying to get the bases the same. 8 and 9, those also involve an exponent, but they're different than the ones we looked at so far because they have what's called a rational exponent. They're not considered like from the exponential function. That would have to have a variable in the exponent. These two have exponents, but they're strictly numerical values. So our strategies are going to be different. Anytime you have an equation with a numerical exponent, a rational exponent, your job is to isolate the exponent and then undo it. So I'm going to do number 8. So I'm trying to isolate the exponential portion here, which would be right here. Okay, so I'm going to start by dividing by 2. Once the exponential portion is isolated, then the next strategy is to undo the exponent. So if it was squared, I would square root it. If it was cubed, I'd cube root it. But for a rational exponent, you want to raise it to the reciprocal power. The reciprocal of 2/3 is 3/2. So the idea is exponent rules tell you that a power to a power, they should be multiplied. And when you multiply reciprocals, you get 1. So the left side is just x plus 2. Over here, you have to recall how to evaluate with a rational exponent. So this rational exponent is read as power over root. So 25 to the 3/2 power means the square root of 25 to the 3rd power. 3 is a power and 2 is the root, square root cubed. So even though it doesn't appear that I took the square root of both sides, that rational exponent actually means it's a square root. So if the denominator of the exponent that you raise both sides to is even, that means you're going to need plus or minus. If the denominator were odd, then that would be like taking an odd root of both sides, and you don't need plus or minus. So the square root of 25 is 5, and 5 cubed is 125. Again, if I raise both sides to an exponent with an even denominator, I'm going to have to use plus or minus. Isolate x. Don't leave your answer like that. That can keep going. -2 minus -125 and -2 plus 125 give you your two solutions. So 9, you're going to do the same thing. You're going to isolate x to the 3 halves, and when it is, then you can raise both sides to the reciprocal power. 10 is just more like what we were doing before 8 and 9. Okay, so then we get to the last type of exponential for number 3 and number 11. I was looking at that 3. Number 11 and 12, and then there's some more to follow. So this is exponential, like we started with, except it's impossible to get the bases the same, right? There's no way to rewrite a 3 and or a 61 so that they have the same base. So we need another strategy. So there is a simpler way to do this particular one because there's not a whole lot going on. The more complicated they are, though, you'll need a different strategy than writing this as a logarithm and using change of base formula. That's sort of the easier way. If you have a good understanding of logarithms, then you'll know what that means. So we're going to use the strategy that we're going to have to use when they get more complicated. So if it's exponential and the bases cannot match, then you put a log or a natural log on both sides. So when I say log, that means common log, log base 10. If the base on either side was e, we would have to use natural log. But because the base on either side is not e, we can choose natural log or common log, and it doesn't matter. If you put in your calculator, like you calculate, say, common log 5 divided by common log 2, you get the same exact result as if you do natural log 5 divided by natural log 2. So the choice is yours. So usually students choose common log if they have a choice. So I'll do that, just putting a common log on both sides. Remember, you can do anything to an equation as long as you do it to both sides. The next step is to take any exponents on either side and expand them using your properties to a coefficient. And then I'm just trying to solve for x. So my next step would be to isolate x by dividing both sides by log 3. So then this is called calculator ready form. This is your exact answer. If you were doing an application problem and it actually tied to something real world, then you would probably keep going and put this in your calculator so you could get an equivalent value, but we're just going to keep it like this. Okay, so then for 12, it's similar, except first thing we're going to do is divide by 5. Then we're going to do exactly what we did in number 11. For 13, so it is exponential because we have a variable in the exponent, but we have to isolate that. So I'm going to add 5 to both sides. So you want to remember that e is a value, just like pi is a value. So it looks like a variable, but it isn't a variable. It's an irrational number. So we're still just solving for x. So after you isolate it, then you want to treat it like we did in number 11. It is exponential, but we can never make the bases match, right? What are you going to do to make a base of e and a base of 10 match? Nothing, just like you couldn't make the base of 3 and the base of 61 match. So here I had a choice, natural log or common log, and I chose common log. Here I have a base of e, and so I want to put a natural log on both sides. The reason why you want to use natural log is because one of your properties of logs is if the base of the log matches the base of the exponent, then they undo each other, cancel each other out. So natural log stands for log base e, and e is the base to this exponent. So the base of the log matches the base of the exponent, and they just cancel each other out, and you're just left with x minus 1. And again, remember, I'm just solving for x here. So x equals the natural log of 10 plus 1, which seems like a really odd answer, but you can pop that in the calculator and get a value. Let's see. For this one, you are going to start out like we did in 12, like you're just going to start moving things away from this, and then you'll put the natural log on both sides. Okay, so then for 15, it's still exponential. We need to work on isolating this. So I'm going to start by subtracting 5. And I'm in the position I was previously. It's exponential, but there's no way to ever make these two bases match. So since neither of the bases are e, I can choose common log or natural log. If either of these were e, then I would have to use natural log. So again, students usually choose common log, so I'll go with that. I'm going to put common log on both sides. And then any exponents get expanded to coefficients. So have 1 over here. So I'm going to move x minus 7 out front as a coefficient. If the exponent that you're changing to a coefficient is a binomial, you want to distribute that. So I'm going to distribute this like that. So it's going to come x log 16 minus 7 log 16 equals log 19. So I'm just trying to isolate x now. So I'm going to add this to both sides. And then divide both sides by log 16. So not the best answer, definitely not nice and neat, no integers here. That's considered calculator ready form. If you had chosen back here to use natural log on both sides, then all these common logs would just be natural logs. Again, that's considered calculator ready form, that you can just type that in your calculator if you want an approximate value, but we just leave it like that. So let's see, this is more of the same. No way to get the bases the same. Choose log or natural log on both sides. Same here. Pretty much the most complicated that you're going to have is if both of the exponents are binomials. And so this is about as complicated as that's going to get. You have to use some algebra skills. So I'm going to do that one with you. So it's exponential. No way to get 7 and 3 the same. So I'm going to do log or natural log on both sides. I'll put log, could be natural log. Any exponents move out front. They get expanded to coefficients. Any exponents turned coefficients that are binomials have to get distributed. So this becomes 2x log 7 plus 1 log 7. And over here, x log 3 minus 6 log 3. Okay, so how's this one different than 15? Because 15, once I distributed, I only had x in one place, so I just had to start moving things away from it. In this one, I have an x on the left and I have an x on the right. And remember, I'm trying to isolate and solve for that. So that's a problem. I need those together in order to eventually isolate them. So if you have two x's in two different terms, but you're trying to solve for it, then you're going to want to get those on the same side. So the two terms that have x's, I'm going to put on the same side, and the two terms that don't have x's, I'm going to put on the same side. It's completely up to you which side you move the x terms and which side you move the non-x terms. You can kind of think that through in terms of what am I trying to say? Signs, like what you want to be positive and negative. So it doesn't really matter though. So I'm going to keep this here. I'm going to subtract this. And then I'm going to move this here, which means I have to subtract it. The order over here on the left doesn't matter. So they're both negative. So if you had made a choice to move things to the opposite side, you would have the opposite signs. Like this right now is the only positive term. If I had moved things to the other side, that would be the only negative term. Okay, once you have the two terms that have x on the same side, that becomes a GCF that can be factored out, right? Both of these terms have x as a common factor. So I'm going to factor x out. And then I can just divide by that whole quantity to isolate x. And as I said before, you could make a different decision about which sides things move to. So you could have made a different choice, or you could go back through and change the signs to the exact opposite. So you could change this to positive, 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 and make this the only negative if that was important to you. This is, again, a calculator-ready form, super complicated looking. No need trying to make it any simpler than this. If I wanted an approximation, then I would put that in my calculator. Okay, let's see. So this is going to be the same. This one, you need to use your exponent rules to turn this into a single term by adding these exponents before you do a log or natural log on both sides. And then the last couple, now these are log equations. So one thing you have to remember about logarithmic equations is that there's some rules surrounding logarithms. The base of the log has to be positive, and the number or the value next to the log has to be positive. So that means that when you solve a log equation, you can have an extraneous solution, meaning that you did everything right to solve, but it still does not satisfy the equation. That doesn't happen with exponential equations. So you do want to, when solving a logarithmic equation, you do want to substitute your answer back into the original equation and make sure that you don't have an invalid base or an invalid value next to your log, meaning that they cannot be, this can't be 0 and it has to be positive, and this also has to be positive. Okay, so if you have an equation with a single logarithm, you are going to write it in exponential form. So when we started with the warm-up, find that back here, when you write a log into exponential form, remember the base of the log is also the base of the exponent, and then the other two values just swap sides. So that's all that's happening here. You're going to write this in exponential form. So 3 will be the base to the exponent, and then the 2x plus 1 and the 4 will swap sides. Then it'll be an exponential form, and it should be obvious what to do at that point. So number 20 is going to be similar, except you're only allowed 1 log per side, and I have too many logs on the left. So we use our properties to condense the left-hand side into a single logarithm. So back to that warm-up, 2 logs added, condensed to a single logarithm where we multiply. Then I'll be back in the situation where I have a single logarithm, and I will write that single logarithm in exponential form, and then it should be obvious what to do. And then for 21, this is the easiest of them. So because I have this side equal to 0, then I can move one of the logs to the other side. And just like with exponential, when the bases are the same, you can cancel them out. When you have a log on each side with the same base, those can cancel out, and then you can just solve what's left. Again, remember with a logarithmic equation, you have to make sure that you don't have an extraneous solution, which would mean that an answer that you get, if you plug it back into the log equation, the value next to the log can't be negative. So, and it can't be 0, and so it has to be greater than 0. So you do want to check that. Okay, I hope that helps. I do have office hours later if that's needed, so just check Schoology for more information.